Hello everyone, welcome to Neso Academy. In the previous lecture, we discussed the course overview and importance of VHDL. In this lecture, we will start with the actual concepts of VHDL. This is the second lecture of VHDL programming course, and the name of the lecture is VHDL Fundamentals. Here, we will see the basic ideas behind the language before we start VHDL coding. So, in this lecture, we will discuss the following topics. The very first topic is VHDL basics. In this section, we will understand what is VHDL and how it is used to model digital systems. Then, we will see VHDL as a hybrid language. At last, we will see few capabilities of VHDL. So, these are the topics we will cover in this lecture. So, let's start with the very first topic, VHDL basics. Now, we all know VHDL stands for Very High Speed Integrated Circuit Hardware Description Language. It is used to design digital systems across different levels of complexity, from high level to gate level implementation. It means VHDL allows you to design systems at different levels of detail, depending what you want. Starting from high level, in this, you describe what system should do and not how it is built. For example, if I ask you to make a cup of coffee, no further details, just this statement. Now, this is high level implementation. But if I say, turn on gas, heater heats the water, water temperature rises, and so on, full of details, full of explanation, now this is low level implementation. Let me give you another example to make it more clear. For high level, if we want to add two numbers, then we will write sum equals to a plus b. Over here, we will focus on the functionality of addition rather than the process of addition. But in gate level implementations or in low level implementation, we will design the entire system using logic gates. In the same example of adding two numbers, we will design an adder first using logic gates, AND gates, OR gates, and XOR gates. So I hope it's clear to you now. So VHDL can be used to design systems of any sizes and complexity. At lowest level, we can design something very small, like a logic gate, example, AND gate. At medium level, we can design components like adder, multiplexer, comparator, or anything. At the highest level, we can design an entire digital system, such as a processor. Therefore, VHDL is a flexible language. It works for simple circuits, medium modules, and for very large systems. Now, I hope this point is clear to you. So, let's see another function of VHDL. VHDL supports hierarchical design, dividing complex systems into smaller components that can be designed and connected separately. Now, what is hierarchical design? It is a way of designing large system by breaking down it into smaller components. For example, if you want to build a house, you don't build everything at once. You create room separately. Kitchen, bedroom, bathroom, then combine them to make a full house. In the same way, a complex system is divided into smaller components. Components can be of any sizes and complexity based on the system, and each component can be designed separately, then combined together to create a full system. So overall, VHDL helps in designing complex systems in structured and manageable way. So, till now, we saw VHDL as a flexible language which follows hierarchical design. Now that we understand VHDL basics, let us see an interesting way to understand the nature of the language in our second topic, VHDL as a hybrid language. Now, what is hybrid? Hybrid means it is a combination of different languages. Now, VHDL is not just one type of language. It combines features of different design styles or different languages. The different languages are sequential language. In this, we describe process step by step, one line after another. Example, first take input, then the process, then gives output in a series. Then second language is concurrent language. In hardware, multiple operations happens at the same time. That is, parallel execution of multiple statements. Example, adder, subtractor, comparator working simultaneously. Now, this is very important feature for any hardware description language. Then third language is netlist language. It describes how components are connected or wired together, similar to circuit diagram. Example, connection of gates. Just like over here, this AND gate is connected with these OR gates using this interconnection. Then we have timing specification. It allows you to define delays and timing constraints because in real circuits, signals take time to propagate as hardware is time dependent. Let's see the last language, waveform generation language. It helps to define input and output signals. Using this, we can generate waveforms that helps in simulation and verification. And using those waveforms, we can check the correctness of the code. Therefore, VHDL is a powerful language that combines sequential execution, parallel hardware behavior, netlist structure, timing specification, and waveform simulation in a single framework. Now I hope you understand why VHDL is called as a hybrid language. Now, we are done with our first two topics, VHDL basics and VHDL as a hybrid language. Let's see few capabilities of VHDL. In this section, we will see few powers or few capabilities of VHDL. The very first capability is VHDL acts as a communication medium between chip designers and EDA tools. Now, EDA tools, electronic design automation tools, are specialized software, hardware, and services used by engineers to design, simulate, and verify electronic systems. Now, VHDL acts as a link between these EDA tools and chip designers. Now, designers can use multiple software tools like Xilinx Vivado, Intel Cortex Prime, GTK Wave, and ModelSim to create a design. Example, a chip vendor can provide VHDL description of a component to a chip designer. Now, a chip designer will use those descriptions to create a design using any of these EDA tools depending on the design requirements. So, in this point, we understand that VHDL acts as a link between chip designer and EDA tools. So, I hope it's clear to you. Let's see the second capability of VHDL. VHDL supports flexible design methodologies with multiple design approaches. Now, using VHDL, we can design systems in different ways or using different methodologies, such as top-down design. Start with a big idea, then break down it into smaller components step by step. Then we have bottom-up design. Start designing the smaller component first, then combine them together to create a full system. In the last, we have mixed design methodology. In this, we use both the approaches. Design some components from top, some components from bottom, and even some components using both the methods. Now, this makes devices easy to manage and easy to debug. So, in this point, we understand that using VHDL, we can design systems in different methodologies. At last, let's see our last capability of VHDL. VHDL is technology independent, enabling portability across different platforms. It means we can implement the same design in FPGA boards and CPLD boards. Now, we all know field programmable gate arrays and complex programmable logic devices are reprogrammable devices, and FPGA boards are used in complex high-power applications, whereas CPLDs are used in simple low-power applications. We can also implement the same design in ASIC board, Application Specific Integrated Circuit. As the name suggests, it is a task-specific board. For example, we have Bitmain Antminer board. Using this board, we can mine bitcoins. Now, this point explains that VHDL designs are portable and reusable. So, I hope you understand the capabilities of VHDL, which means we are done with our last topic, capabilities of VHDL. So, in this lecture, we saw VHDL basics, VHDL as a hybrid language, and capabilities of VHDL, which means we are done with this lecture. I will see you in the next one. Thank you.